But apart from that, also assignment 7 is very easy if you see the hints. So I made a hint video. So if you just look at this video, you'll know exactly what to do, and you can do assignment 7 in 1 hour. Like if you, the bonus question is difficult, but nothing is difficult in today's world. But just that the assignment 7, the first 2 questions, I showed you exactly what you need to do. And the first 2 questions are going to be on the final as well. At least 1 question from question 1 and 1 question from question 2. So you should do assignment 7. And I give away, like, I exactly show you how to do it in the video. So yeah, that. Messages, right? I saw some messages on Zoom. No. Hi, yeah. It would be nice if he's recording, but if he provided me the recording, that would be nice. But no worries, it will take me 20 minutes to just run over last class. Not today. Another thing you would see on the modules that in today's class 20, I provide the docx and the PDF file for you to practice these final problems that are based on today's lecture. So, and I'm going to solve them with you in today's class. So I provided the solution in the beginning, like I do for all of my practice questions. But that's, I think, okay, I have a downloaded version of it. So I'll just, okay, so I provided the solutions in the beginning, and I kept the questions at the end. So here, from here, same questions, but fresh for practice. So another thing I want to mention, that although I taught before, I taught in my own country and in my own time zone. So my gamer friends, they used to play at night, but now it's their night. So like lots of pop-ups, but a suggestion, if you want to turn off notification, you can do it. Press here and then turn off all notifications before you ever take classes in the future, or for important meetings or presentations. Yeah. So I'll start today, but in my next course, I'll do it every day. So, okay. How many of you are taking 407 next term? Any of you? Okay, 1, 2, 3. Yeah. So see you guys in 407. But yeah, you'll see me again. I'll have office hours, and I'll have like after the exam, there will be an office hour, or you can email me your concerns with the grading and all that. But let us start today's topic. Ooh. So here, today's topic is on memory hierarchy and caches. Here are some useful tutorials. Basically, the videos here, they demonstrate the concepts in a more visual way through animations, which is nice. Basically, 1, 2, 3, 4 covers everything what I'm going to teach you today. The less important part is if you want to know extra, like if you have but 1, 2, 3, 4 will be helpful for your exam. And 5, it's not related to our, it's not included in our syllabus. It's goes beyond that, but you can watch it for your own knowledge. But we all know that hard disks and CD-ROMs are secondary memory, right? So what are primary memories then? Primary memories are internal memories. Anyone can name the primary memories? RAM cache registers, right? RAM cache registers. Now, the main memory, which we call as RAM, can also be, you know, the sticks that we buy and put in, the 4-slot sticks. Some processors have 8-slot, 32 GB, 16 GB. My one's 8. I don't know. I stopped worrying about the RAMs. I stopped playing games. But those RAM sticks, those are actually DRAMs, which is dynamic RAMs. And they are the concept of how they represent 0 and 1. We know everything has to be represented in 0 and 1s, right? So how they do it is they use a capacitor. So you have 2 plates, and if you want 0, what the capacitor does is, if you want the value to be 0, you put negative values here, like positive values here, right? Positive values here, and then this value becomes all negative. So that represents a 0. So you use a capacitor. But cache, on the other hand, is and the reason why this is dynamic is because over time, this charge, it leaks. Okay, this leaks because you provide this charge positive, but over time this charge leaks. That's why it's dynamic. Yes. Yeah, leaks and discharge over time. So that's why it's dynamic. Whereas for SRAM, it's for cache, we use SRAM, which does not have this leakage of values. So it's called static, and we use a flip-flop. Flip-flop is a circuit that stores a bit. So let's say if you want to store 0 or 1, you can put in the designated input and you can get either store a 0 or a 1. But because it uses registers, like it uses this integrated circuits, these are more expensive, but faster. So DRAM, you need a periodic charge in order to maintain the data, as you said that it discharges, right? So you have to refresh it. And over time, you have to keep refreshing it so that your data doesn't leak away. And if you see the memory hierarchy, at the top, you have the registers, which are the most costly and fastest. Here you have cache, which sits really close to the processor. So if you have the processor, you have an onboard, like inside the processor, you have a cache. You also have a cache outside it. You have a shared cache. Like you have different types of caches. But cache is more costly than a RAM, which you buy. So you buy the DRAMs, and the further you go, the more storage you can have, right? Because hard drives are big, right? But RAMs, it's very hard to imagine a 500 gigabyte RAM, but 500 gigabyte hard drive is standard and cheap. But hard drives are slower. As you move up, it becomes more costly to build those hardwares. You can also see that here. So L1 cache is the cache which is inside the processor. L2 cache sits right outside the processor, like here. And the L3 cache or like L4 cache, those are shared by all the cores. If your processor have 4 cores, then all of them will share the L3 or L4 caches. And as you can see that as you go down, the size of these hardwares increase, but the time to access these memories, they are fastest for like registers. We didn't put registers here, but L1 cache is like slower than a register, but faster than everything below it. And as you can see that the time to access data is increasing, and you have an enormous amount of time to access something from the hard disk or SSD. Any question on this? Yes. Faster than a hard disk? Yeah, but significantly slower than a RAM. So here is the diagram. We have the registers inside the processor, the SRAM or the cache. Like the registers are the smallest. They have one-to-one interaction with the ALU, right? They directly can feed values in the ALU registers. If the value you need to use is not within your registers, you have to fetch it from cache, okay? And if it's not in cache, you can fetch the value from main memory to register, or if you are frequently using a value, you might want to store it in cache. So you have two options here. And finally, you have an option. You never use directly from disk to register, okay? If you want to use something, you put it in RAM and then you use it. Another thing is you saw you see this is persistent, right? This is volatile. What does that mean? Can anyone say? Yes, you raise. Yes, so when your computer is turned off, these have the data, okay? These hold the data. And now you might ask, what's the flash drive, right? I haven't seen a flash drive. So it could be, it's rarely used, but it could be on the main board. You know, main board, the motherboard needs some values to store, right? And it needs to keep it persistent, or how is your computer going to know what to do? So some flash memory is that memory, could be a flash memory in your motherboard, some information that it needs to run it. And your question? No, in this case, volatile means when your PC turns off. uh, uh, and also this is ever changing. So like uh, the example that I gave before, let's say Yeah. Let's say you're using Google Chrome, right? So now your RAM will be occupied with the information of Google Chrome. But let's say you have the Google Chrome open in the background for 5 days, right? So your volatile and intelligent RAM will know that this Google Chrome has like really low chance of getting opened, and it will leave it on the hard disk. And its place on the hard disk is like more or less permanent unless you move it. But in the RAM, it's based on supply demand. So in that case, it's volatile. Yes. Yes. So BIOS can be stored in the flash memory. Yeah. And you have Raspberry Pi, those have some like microprocessors, they have their own flash memory to store things. They can have flash memory. But uh, I said one thing, that when you are using things from the RAM, you have two options, whether to put it in cache or directly use it from the RAM. Uh, so in order to do that, you have principles of locality, and you have two principles. Basically, uh, what value should we store? What value should I store, right? So let's say we can easily describe this in a for loop. Int I equals 0, I is smaller than 100, I plus plus, and array of I equals to 7. Nice. So in this case, when we are running this code, you see I am using I a lot, right? So it would be a good idea that the thing that has been accessed will be accessed again soon. Most of us write programs that way, like we keep on using I multiple times, right? So it's a good idea to store I. Temporal means that relates to time, and over again I will be using I for this for loop. So that's temporal locality. So the thing you're using once, you have a probability of using it again, the same thing. And another thing is spatial locality. So you accessed A of 0, right? So there's a possibility that you are going to access A of 1, A of 2, A of 3. So when you fetch A of 0, it's a nice idea to fetch its buddies as well. So that's the idea. Fetch its friends as well. If you're, because you have this spatial locality where if you access a word, you are likely to access nearby words. And you take your decision what to do, where to. You want the most access values to be here, but registers are costly and limited. In MIPS we have how many registers? 32. Yeah. So then you can have a bigger cache, you can have a bigger L2 cache, you can have a bigger RAM, like 32 gigabytes times 4. And you have anything you can put in RAM, you have persistently in the hard disk or SSD, in the secondary memory. Now, who moves the data across these levels? So another question. During the beginning of this course, some people asked, how is knowing this going to improve my task completion time for my algorithms, right? So you can actually define how many, what's going to be the block size or the page size, which means, like I said, when you get a data, you get its buddies or friends as well, right? So there's programming languages, there are options where you can define the number of its buddies or friends, right? So you can define the size of the block. So here you go. This is one example how this course will help you. Yes. You have to access something, but it's not in your cache. So have to go to RAM. That's a miss. You have to go to the RAM. You don't want to go to the RAM. It takes a lot of time going to the RAM. But it's on the next slide. But here, normally registers, they are determined by the compiler. Maybe if you are an assembly programmer, you sometimes manage what sits in the register. For cache, it's controlled by the hardware. So your device has a hardware, the hardware has its own algorithm, and based on that, it puts value in the cache. The main memory and the disk, the operating system determines what should be in the RAM and what you don't need now from the hard disk or the SSD. So block is the number of buddies you take along with access data, the minimum number of unit that you can present in a cache. So mainly, you cannot take one person. If I take you, I have to take your buddies with you. If the block size is 5, if I choose you, I'll choose 5 people around you. That is basically the block size or the line size. You have your cache, right? And let's say that my processor needs a value from a specific address. So let's say the address is FFFF, right? Just imagine if it's in the cache, if it's, let's say this is the cache and this is the RAM, which is bigger, right? Let's say the RAM is bigger. RAM is big. And the cache, it's small. But if the value is present in the cache, then it's a hit. If the value is not present in the cache, it's a miss. And then you can choose to take the value directly from RAM, or you can put it in the cache for future use. And there are some formulas of hit rate, miss penalty, but we don't have any questions on these formulas. So no maths from, there are maths, but not for our syllabus that we cover in this school. Okay. So the organization of cache, there are 3 approaches how you can take the value from the RAM and put it in the cache. And these 3 approaches can also be called 3 algorithms. So you have 3 algorithms to do it. And from this part, let's first look at the directly mapped cache. We'll look at all 3 algorithms, but let's first look at direct mapped cache. So here is your RAM or main memory, right? And here is your cache. Now you can see you can see the cache further extends from here. It's not like only this part. This is the like smallest unit of the cache. So it's a block of a block of the cache. And remember, I said when you access one value, you have to access its friends as well. So at one point, you can put like this smallest unit of block inside your cache. So you have the data. In our case, data is 32 bits, right? And let's say the memory location is 0, 0, 0, 1, 1, 0, 0, 1. Okay. So what will be the tag in this case? So what will be the tag? Basically, the block size here is 4, right? So how many different values can we define with four lines? I have 4 values here, right? And with 4 values, I can define 4 different locations, right? So when you take this one, when you take this location, let's take this location. Let's say it's this, right? But you take the whole thing. That's why this is your tag. And whether it's 0, 0, 0, 1, 1, 0, 1, 1, doesn't matter. I'm taking his friends as well, and I'm taking 4 friends. Okay. So the block size 4 means I'm taking 4 friends, and if your processor wants to access this value, and in the next iteration it wants to access this value, which can be 1, 1, you already have it in the cache. It will be more clear when we do actual exam questions. But just remember, for the directly mapped cache, you check what's the size of the block. In this case, it's 4. So apart from the 4, whatever the address you have is your tag. And you take the whole, like you take 4 of these values in your cache. Any questions? Let's just quickly go over this and get to the final questions, right? So directly mapped. Okay, the lecture doesn't include the other forms, but I'm going to show them in the question. The other two, right? So you have the one. Oh, yes. So we have gone over the direct map cache, which is if you have a 4 block size of 4, you just take this part out and the rest of it is your tag. Let's look at fully associative cache. The fully associative cache is an easier version. So in this fully associative cache, you just have the block number. So let's say you have block 0, block 1, block 2, block 3. If your cache size is if your total cache size, let's say your total cache size is 8. So you'll have 8 values here. So 4, block 5, block 6, block 7. So you'll have 7 boxes here. Now, you don't have any tags. So no, like not in the general sense. So if your block size is 4, right? In each of the block, you will have 0, 0, 0, 1, 1, 0, 1, 1. So in each block, you can store 4 values. And in the previous one, we had a tag, right? We associated a value against a tag. But in this one, we just put in the remaining values inside. We don't have a specific index for selecting it. So let's say you're accessing A, right? And then you will take out 0, 0, 0, 1, 1, 0, 1, 1. You will, if this 0, 1 is A, you will take its friends as well and put it in the block. But the difference between the associative one and the direct one is that you also have an index for it, like fixed index. So if the total cache size is 8, then you can only put in 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. So here you see when we store a value, this, if this is if the index is 3 bits, then this is 100, right? Then you can only put it here, only here. Okay, only if you're using direct mapped. But if you are using set associate, right, then you can put it anywhere. You don't have a fixed place to put it in. These block 0, you don't have to put it in. The index doesn't have to be 0, 0. You can put it anywhere. But for the direct mapped one, you have to look at the index. Let's say it's 100, and you can only put it in the 100 spot. Where's the 100? So in your cache, you will have this arranged, and you can only put values based on the index. Whereas for the associative, you can put it anywhere. And an improvement of the direct mapped cache is the set associate one, where under one tag, you remember I have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Let's say your cache size is 8, right? Now, a question for you. If this is my index 101, like let's say the index is the this bit 0, 0, this is the offset, and this is the tag 1, 1, 1, 0. Let's say this is my I want to put this value in the cache for fully associate, right? For fully associate, where do I put it? Fully associate. we have three options: direct, fully associate, and set associate. For fully associate, where should I put this value? And anyone? The first, yeah. Anywhere, and the first, normally you in the first option, because you can go anywhere for the fully associate. So fully associate, you go anywhere. So, and normally in our case, in our exam, we'll be going to the first empty spot, which is going to be this spot. So A, if we consider this as A, it will go into, this is the fully associate way where A would be, okay? Where will it go if we use direct mapping? Remember, for direct mapping, it will be based on the index, the cache index. So where will we put it for the direct mapping? Yes, because the index signifies where we have to put it. So we have to put it here for the direct mapping. Now, in some cases, 10110, let's write 100. This is a new thing called B. 101 is the index and the offset is 01. Now for ones, let's say this is B, okay? Now we already have something in A, right? Where should B be placed? For fully associate, where should B be placed? I have another one to put in the cache. B, which has an index of 101. Okay. Where should B be placed for the fully associate algorithm? 001. The next free slot, B, here, right? We look from top and down. We start counting from 0, then 1. Okay. And this is for if we are following the fully associate algorithm. But where will we place it for the direct mapping algorithm? It has an index of 101. Where will we place it? No, we'll kick out A and put B in its place for the direct mapping. A just goes away. Yes. But there's a third one where it's a n-way associate, n-way set associate algorithm, where you don't throw away, it combines both fully associate and direct mapping. So how? So you have, if it's a 4-way, then you have 4 places where you can put it. So this is for direct mapping, you cancel out B and put it in place of A. But for the set associate mapping, you can put it anywhere inside this so each of the indexes will have multiple places where you can put stuff, and it will be determined by n. So in this case, we have 4 places to put stuff, and this is a 4-way set associate. This is 4-way set associate algorithm. Everybody is okay with this? We'll go over it one more time because questions will be on this topic. This is the topic you need to be aware of when you are doing it. So let us do it in a like a free. Okay. So in two-way set associate, you can see that you have one spot for A, one spot for B, right? This is set associate. And you can have four-way where you have four places. So you can put A, B, C, D, even if they have the same, they have to have different tags, but the same index, they can be put in these four spots if you use four-way set associate. So just to go over this thing again, because this is important for the exam. I'm going to show you how the exam questions will look like, but let's just get it clear. So let's say you have a 8-bit address. Let's say it's 0, 1, 1, 1, 0, 1, 0, like 4 here and 4 here. Okay. Now, let's say your block size is 4. So what will be the offset? The offset is dependent on the block size. So offset is, if offset is n, then 2 to the power n equals to 4, which you get from block size. And you can find out n is 2. So you have your offset here. And let's say you have been given in the question that the index, the set index or the block index, the index is 2 bits. 2 bytes, actually. No, 2 bits. Okay. Index is 2 bits. So if you have 2 bits, right? 2 bits of index, can you say what is the size of the cache? Because each index will point to one address, like one block. Each index will point to one block. So what will be the block? What will be the size of your cache? How many blocks will your cache have if you have 2 bits to represent it with? 4, because 2 to the power 2, you get 4 options, right? So you have 4 options to choose from. So 4 blocks to choose from. So you'll have block 1, block 0, block 1, block 2, and block 3. 0, 0, 0, 1, 1, 0, 1, 1. And this will point to a block, and each of the block will have four data points, like 1 for the data that has been accessed and 3 for its friends. Okay. So this is your cache size. It has 4 blocks. Now, let's assume that this holds the value A, right? Now the question is, if we use direct mapping, where will the value go to? Where will the value of A go to? in this cache, this is your cache. Inside cache, for direct mapping, where will the value go? Block 1, yes. And what will happen with the other empty spaces? Let's say A has this spot, right? Because it's 0, 0, 0, 1, 1, 0, 1, 1. What will happen with the other spaces? Will it be empty? No. You put it's for his friends. So you have 0, 0, right? You can't only bring one thing. You also have to bring its friends, 0, 1, 1, 0, 1, 1. So let's say A's friends were B, C, and D. So you have to put it inside the cache because that's the principle of locality, right? If you get one value, you have to get its friends as well. Okay. Now, if it was fully associate mapping, where will we put the value of A and his friends? 0, 0, because the first empty spot it gets for fully associate, it would put it in the first empty spot. Okay. You don't care about indexes in that case. You just look at the offset. But now we want to put another thing which has the same, let's delete this. Let's say 0, 1, 1, 1, 0, 1. This is going to be interesting, okay? 1, 1. Is it the same value? Are these two values exactly the same? No, they're not the same. This part is different, right? This part is different. What will happen? Let's say I have something value, an unknown value X here. What will happen if I want to access the unknown value X? What will happen? Anyone? What should we do for direct mapping? I need an answer. Kick off A, right? But wrong. Because it's a hit. It's a hit. Because you see, if the tag matches, the tag matched. So it's a hit. So you don't, the unknown X is actually D. You already got him. It's its friend. It's A's friend D. So if the tag matches, then you don't have to bring it because you already have it. It's a hit. And now for the question that you wanted to answer, if 1, 0, 0, 1, then always ran out of space. Okay. 1, 0, 0, 0. And if the index is this is the index and this is the offset, 1, 0. What will happen if we use direct mapping? What will happen if we use direct mapping now? It's the answer you gave. Kick it out because we don't have space for it. So let's say it has F, right? So F will sit here and will also have to bring its friends, E, F, G, H. We have to let go of A and its friends and bring in F and its friends. E, yeah, just bring in the friends and F, G, H. So that's how cache works. For direct mapping, you have to kick it out. For fully associate, you put it anywhere, free location, anywhere you have. And for set associate, it's similar to direct mapping, but it set associate is exactly works like direct mapping, but you don't have to kick out. You have, based on the number of sets, you have more spaces. So if it's a two-way set associate, you have two spaces to put it in. But if you exceed two, then you have to kick out one. Now, the final part of the lecture is how do we kick out, which should we kick out, right? So, first in, first out, the first in, first out, you could use that. For our exam, we are going to use least recently used, okay? So the thing that we recently changed or accessed or made changes. So we are going to use this in our exam. And these ones frequently used, right? So can anyone think of a way to kick out the least frequently used? Just a programming approach to kick out A or its friends, B or its friends, based on what has been used less frequently. Yes. Yeah, just. Yes, F would replace C. I saw that and I fixed it before anyone could notice. Yeah. Yeah, I when I was putting it in, I put it in, you see, yeah. So that's the answer for this question. I recognized it. Okay. So you were saying count the frequency, right? That's one way. Another way could be you have a timer, right? Like you have a clock. Every time you use it, you reinitiate the clock to 0, and then the oldest guys, they have to leave. So but that's an approach. This is an approach. There are countless approaches you can take, right? But what has been found is that this approach, the least frequently used approach, is not good. The best approach is the least recently used. Like you could use something 1,000 times 5 years ago, right? Doesn't mean you're going to keep it in the cache. So they have found that least recently used is the best. But what they also found is if you randomly kick someone out, it's equally similar. And it's really hard to implement this in a hardware level, right? So normally what processors do is randomly kick out someone, especially if you have like a budget, like if you have you don't need to implement this, just kick someone out, it will be good, okay? So, but in our exam, we'll use the least recently used approach. Now, talking about exams, let's recap. Let's look at what I showed here. So the size of the cache, it must be 2 to the power n. So it can be 1, 2, 4, 8. So if you have a quick question that the block size is one word means 4 bytes, okay? And the cache size is 32 bytes, then how many cache entries would you have? Like how many blocks will you have? Cache entries are like blocks. So it's going to be 32 by 4. So size of the total size of the cache divided by the block size. That will be the number of blocks you have, or the number of cache entries you have. What will be the cache index? So if you have 8, right? How many bits do you need to represent 8 values? How many bits do you need? This is important for the exam. Yes, 2 to the power 3 is 8. So you need 3 bits of index to point at your different cache entries. Okay. Now for n-way associative set associative algorithm, you have multiple blocks per set, right? So for a 2-way set associative algorithm, for every set, you have 2 blocks. And if the size of the block is 32 bytes, and it's for a 2-way, then, and if the block size is 4 bytes, then you do 32 divided by 4 into 2, because 4 comes from like the block size, right? But now you have space for A, and you don't want to kick out A, right? You have another space. So you also have to divide that. So 32 divided by 8, 4 sets. So in this case, instead of a block index, we call it a set index. So the set index, if we have 4 things to point at, how many bits do we need to point at them? 2, right? Because four things, it can be 0, 0, 0, 1, 1, 0, 1, 1. 2 bits to point at the 4 things. And so here's a question. If the block size, forget about cache. If the block size is 1 byte, and if you have the number of blocks is 128, and this is fixed, what will be the index? So if you have a block size of 1 and you have 128 bytes of the block size, then you can have 128 blocks, basically. You know, the number of blocks is the size of the cache, so size of the cache divided by the size of the block. In that case, how many values do you need to represent these 128 values? 2 to the power m or 7? You can quickly find that out by log to the power 2 of 128, but we know it's 7. 2 to the power 7 is 128. And if we consider the rest of it as tags, so it's going to be 32 minus 7. But it becomes a bit difficult when you have a larger block size. So one word means 4 bytes, right? So 128 bytes divided by 4 bytes. Now you have 32 locations to point at. How many bits do you need to point out 32 locations? Like 2 to the power what is 32? 5, right? So the index size, the IDX or the index size is going to be 5. And normally we delete the address. The address is 32 bits. From 32, we delete the index and we get the tag. But because the block size is 4 bytes, we need an offset to point at those bytes, right? So we need to point at these 4 values. How many do we need? We need 2. Offset should be 2 here. That's why we also, and I marked it with a yellow color so that you don't forget. You also need to negate the offset to get the tag, the number of address bits that are going to be considered as a tag. And here's another example. If it's 4 words, so 16 bytes make 1 block, and you need to point at those 16 bytes. So you need an offset of 4, and you also have 16 here. So the number of blocks will be 8. So you also need to point at these 8 values. So this, to point at these 8 values, you have the index, which is a size of 3. But for the offset, you need to point at 2 values. No, you need to point at 16 values. That's why the size of the offset is 4. And then the size of the tag is 25. I'm going to quickly go over these questions. I have a final solve tomorrow as well, right? Not tomorrow. The next class is also a practice for final. So if you have any questions, come back on me on that class. But let me just quickly finish question 2, question 3, and question 4, and question 5. Okay, I'll do it quickly. So in this question 2, the cache size is 256, and it's a 4-way. So 4-way cache means it's a set associate. So it has 4 sets. So here, 256 bytes, 4-way cache, and a block size of 1 word. 1 word means 4 bytes. 1 mon is 4 bytes. What bits used for the cache index? Which bits used for the tag? How many sets are there? So we first have to find out how many sets are there. It's similar to the formula, number of cache blocks, number of cache indexes, which is you get for direct mapping. But because it's a set associate algorithm, you have to find out the number of cache sets, which is cache size divided by the set size. Now, the set size, the cache size, it's given in the question, which is 256. And for the set size, it's how many sets do we have? 4 sets, right? And what's the size of each of the block? 4. So 4 multiplied by 4, this is how many sets? Number of, like, how many 4-way? So 4. And this is the one, this is the block size. Yes. So that's why the number of sets is 16. And I just drew it out. That every block, it will have, if the value in itself, it will have 0, 0, 0, 1, 1, 0, 1, 1. You can think of it as space for A and its friends, right? A and its friends. You have 4 spaces for A and its friends, and because the number of sets is 16, so you have 16 values. And if it's a 32-bit value, then the first 2 bits are for the offset, because you need to point at which set you are referring to. No, you need to point at which you need to point at which value you are referring to within here 00011011, right? So this block size determines the offset. Because the block size was 4, only the block size determines the offset. Because the block size was 4, that's why the offset is 2, because we need 2 bits to represent this 00011011. But the set index, we have 16 sets here, right? So for the set index, we need 2 to the power 4, or like 4 bits to represent which set we are referring to. That's the answer of question 2. Let's look at the answer of question 3. So when you get this question, the first thing you have to do is bring a calculator, okay? If you bring a calculator, you can quickly find out what these values are. And you quickly write them down. Once you have them, you look at the question. So the question asks, you have 8 blocks. So these are not the 8 blocks. These are just the number of instruction. And by coincidence, they're 8, but this has nothing to do with this. No, this 8 block is what you have to draw out yourself. So this is the cache that you draw out. And this is a really easy question to get marks on. You just draw out the 8 blocks. And because this is a direct map, so we know that based on the cache index, we have to put in where the value is going to be. What is the size of the block? The block size is 1 byte. So we don't need an offset. So offset, we don't need it because block size is not 1 word, but 1 byte. We don't have to point at it. So no offset required. But what we do need is we have 8 locations to point at, right? We have to point at 8 locations. How many binary bits do we need to point at 8 locations? 2 to the power 3. So 3 bits, right? So that's why the cache index is going to be the last 3 bits. And in your question, you just have to write out the last 3 bits here and the tags that are separated here, okay? So just do that. And now we have to check whether it's a hit or miss. So I'm going to do it in front of you. So 0, 1, 0. This is a direct map 1. So for direct map 1, let's do it, quickly do it. I think after doing this, we have to solve the next 2 problems in the next class. But just let's slowly do it. We have 0, 1, 0. Where should we put it? In 0, 1, 0. Yeah, 0, 1, 0. A, like number 1. See, I have referred this as number 1, number 2, number 3, number 4, and so on. So I put this. Was it already in the cache? No, because you just started your computer. The cache is empty. So when you start your question, the answer will be always a miss. The first one, you just write miss, you get a point. Yeah. But the second one, it's colliding with this one, right? And it's a direct mapped one. We don't have space for it. We have to kick it out. Unless, hey, no. Because in this one, there's no offset. The question had to be different. And there are some questions where there's a hit, but this can be a hit because there's no offset, right? The block size is 1 byte. So the only way it can be a hit if it's exactly the same value. So this is it exactly the same value? No, miss. Because this is the cache index and this tag doesn't matches. This and this tag is different. Okay. So it's also a miss. And you would see the next one, it's also 010 and the tag is different. So it's a miss and we have to throw it out. So we put in 2, but we have to throw out 2 because we don't have space in direct map. We are throwing it out as well. And this is a miss. This is a miss because this is a new cache index, 100. And number 4, we put in 100. Number 4. So, and then does this exactly match what's in our cache? What's in our cache? In 010, we have 3, right? So in order to be a hit, this exactly has to match this. Hit, does it match? No. So it's also a miss. And this is a new one, but 5, right? So 5 will now replace it because for direct mapping, we don't have more spaces. And for 6, 110. For 6, we haven't used 110, so put 6 here. And you would think that this is a hit, right? Because it has been used before, but no. The only value we have is of 5, and 5 is not in what's 5? This one, right? This doesn't match this, so it's not a hit. It would be an hit if this was exactly after this one, in that case. But it's now 12:17, and this gives you an idea to practice the other questions and come back next class. I'll explain you the other questions, but it's not hard. But yeah, just go through the lecture, try out the questions by yourselves. I'll solve it next class. Why is there no offset? Yes, because the block size was 1 byte, not 1 word. When the block size is 1 word, you can only have A, not its friends, you know. That's why Julian, there's no offset. But if it was 1 word or 4 bytes, then you have space for A and its 3 friends. But you don't have any space for its friends. That's why there's no offset. Hope I answered your question, Julian. Will the final be similar to the practice final? Yes, the final will be similar to the practice final, but it will have some unseen problems, but it's seen in the slides, but unseen in the practice exam. I'm not going to directly, everything in the practice final will be in the final, but there will be some extra things.